Okay, so let's get started. I'm Karthik Nanda. I'm a fellow here in Austin, Texas. And today I will be talking about GPipe and training giant neural nets. GPipe, this is a Google project, and it's essentially software. But we'll get into that in a minute. This paper came out late 2018, I believe, and it's, to the best of my knowledge, not publicly available. This tool is something that Google will eventually make available to anybody to use. Okay, so this was a fascinating read, partly because this actually focuses more on hardware implementations. It actually talks about how do we accelerate training giant neural networks, or how do we accelerate developing models, basically. So let's see. This one. There we go. So the outline for the talk today, I'll briefly mention what the issue is. Why is it that Google is working on GPipe? What are some of the prior approaches? Like how do various teams of people in the past and even today actually accelerate the training or development of the model? And what is it that GPipe actually is offering? So the proposed solution. So what essentially is GPipe? So I took a slightly different approach when I was planning this presentation. Rather than talk only about this paper, I decided that it would actually make a little bit more sense to maybe go a little bit deeper and talk a little bit about what the state of the art is and what it is that people are actually doing, in addition to just the GPipe paper, because GPipe itself is actually fairly narrow, and it's just that for me, I guess, in order to understand what GPipe was all about, I had to go back and look at a few other papers, and I figured it probably would help the audience as well. So what is the issue? And this is a quote from the paper itself. Memory has increased. So the amount of memory that is actually available on, let's say, GPUs or on typical accelerators that are used to run training, that memory capacity has increased by 3x over the, let's say, the last 3 years. Whereas the number of parameters, or in other words, the amount of memory that is being used, has increased by over 36x. So for example, GoogleNet in 2014, which won the ImageNet Challenge, had about 4 million parameters. And in 2017, the network that won the challenge had 145 million parameters. So all of these parameters have to be stored in memory. And it's not just the parameters that have to be stored, it's also the activations. So for example, on that figure in the lower right, imagine you've got 4 different layers. In order to compute everything, you have to, for example, if you do the forward pass on the gray square here, you actually have to store those activations for when you actually compute the backward pass. So if all of this was being done in one accelerator, you would have all the parameters of the 4 layers, as well as all the activations that have to be stored before you can update the gradients. And all of this storage is essentially in memory. So what are some of the prior approaches? So one possible way is to recompute the forward activations during the backpropagation calculation. And what this does is it trades compute for memory. So the activations are no longer stored. And so in the previous slide, in this image, none of these arrows that go from the F to the B, none of these values need to be stored. But then we are trading that for computation. So in other words, we're actually doing the forward computation twice because we have to recompute those activations during the backward propagation step. So we're trading compute for memory. The second option that people have tried is memory swap. And since there isn't enough storage on the accelerator, the activations are copied back to the CPU or the main memory. In other words, they're swapped out, essentially a page swap, and then they are copied them back as and when required. The problem with this is it's slow. And anybody who's ever run into too many processes running on their machine, slowing down their machine, knows exactly what this means. So it's that anytime you don't have something in your cache, so-called cache, you have to go and hit the main memory, that latency is long. And so the amount of time required to do that is long. So anytime you're actually sending stuff from your cache, you're unable to hold the data in cache, and it has to be copied back into the main memory, it just takes a lot longer. So those are two. What are some of the other approaches? So the main second, or the main, I guess the workhorse, every time that we talk about using multiple GPUs, for example, or using, let's say, 256 GPUs to run training of a certain net, the idea is essentially parallelism. So what you're doing is you're actually distributing the load, the workload, between multiple different GPUs. And the word used here is workers, so multiple different workers. So if you have 256 GPUs, you have 256 workers. And then the question is, how is that compute? How is the compute or the computation, the total computation, distributed amongst all of these workers? So there are two main ways. One is data parallelism. Okay, does anybody have a question? And please feel free to interrupt me and ask a question. It makes it more engaging. So if you have a question, you don't understand something, feel free to unmute and go right ahead. Okay, so data parallelism is where each worker has the same model, but is working on different pieces or different pieces of the data. So it's, for example, in this image, you've got, let's say, a batch of 64 images, and you have 8 workers. So each of these workers has exactly the same model, but they're working on just a small set of the 64. So in this particular case, 64 divided by 8. So they're working on 8 images each. What that does is now, instead of one worker working on 64 images, you've got 8 workers working on 8 images, and theoretically at the end of it, they sync up and you get the exact same result. Of course, it doesn't exactly work like that. You're dealing with updating the model, and so there is a significant step in syncing up, but I'm not going to talk about that. The one place where this actually works really well, data parallelism works really well, is the convolution layer. So imagine you've got this big image, we're running multiple different convolutions, and if you have multiple GPUs, then you can run a whole number of convolutions in parallel, right? So that's the general idea. The second, so coming back here, is model parallelism. And one way this works out is, for example, let's say we've got a dense layer, and we say that instead of one worker working on the entire dense layer, we're actually going to split the dense layer between 4 workers. So what we've done here is we've actually split the model. So we've got part of the model given to worker 1 and part of the model given to 2, 3, and 4. And the data is essentially common. Now, it's pretty obvious that these workers will have to communicate between themselves. So worker 1 needs data from worker 2, needs from worker 3 and worker 4, and so on and so forth, because this is a fully connected layer. So in this particular case, there's a lot of communication between the workers. And this particular scheme works well when the number of parameters are large compared to data, right? So, well, what we're doing here is splitting the number of parameters between the workers, but the data is all the same. Whereas in case of data parallelism, we're actually, every worker has the same set of parameters, but the data is split up. Now, another example of model parallelism is where different workers actually work on completely different layers. So for example, on this image on the left, which is the same image as before, you've got 4 workers and you have 4 different layers. So worker 1 works on the first layer, worker 2 on the second, third, and the fourth, and so on and so forth, right? But the issue here is if you actually look at this, in order to compute F1, you already need to have computed F0 and all the way around. And so if you actually plot the execution where the x-axis is time, then you've got F0 computing first, everybody waiting for that. And once this F0 is computed, then this F1 is computed. And then this blue F2 is computed, and then the pink F3, and then similarly on the way back, the B3, B2, B1, and B0. So this is mislabeled. I just copied this from the paper, so it was actually mislabeled in the paper. And once we've done all the back propagation computations, then we do the gradient upgrades in parallel. So anybody who's looking at this, it's pretty obvious that we're wasting a lot of time here, because at any given time, the workers are mostly sitting idle. In fact, if you actually had just one worker, that worker could have done F0 followed by F1, F2, F3, B3, B2, B1, and B0. And the only place where you are actually saving time is in the updates. So this is what GPipe is all about. Now, what GPipe does is essentially pipeline. And so what is pipelining? Well, you can sort of get an idea from this image at the bottom here. But what pipelining does is it integrates data and model parallelism. So it actually has multiple workers, and it is parallelizing not just in terms of the model, but also in terms of data. So for example, in this image, what you see is only model parallelism, but there's no data parallelism. What they've done is then, so I guess if I explain what they've done, that would help. So the key ideas are they're dividing the data mini batch into micro batches. And so, for example, F0 is divided into 4 micro batches, F0, 0, 0, 1, 0, 2, and 0, 3. And different workers, accelerators, in other words, work on different micro batches at the same time. So as worker 1 finishes F0, 0, it hands this micro batch to worker 2, which can then start working on F1, 0, while worker 1 simultaneously is working on the second micro batch. So the dependency here is from F0, 0 to F1, 0, from F0, 1 to F1, 1, and then further to F2, 1. And so at this particular stage, for example, you've got all workers simultaneously working. And then the whole thing kind of goes backwards as well, and then you do the updates in parallel. So workers in the end sync up in exactly the same way as they did previously. And so the gradients are updated when the entire mini batch is processed. I'll stop here and ask if anybody has a question. Let me see the chat. Okay, no questions. All right. So carrying on. So one verbose slide. I'm going to read through this and try and explain this. So what are the key features of GPipe? So number one, GPipe is actually a distributed machine learning library, which uses synchronous mini-batch gradient descent for training. Pretty standard stochastic gradient descent. They use mini batches. They then take these mini batches and they actually split it into micro batches. And then these micro batches are then split amongst different workers. And they use both data parallelism as well as model parallelism to achieve a throughput improvement. Okay. They partition a model across different accelerators and automatically split mini batch into smaller micro batches. And then by pipelining the execution across micro batches, accelerators can operate in parallel. GPipe also inserts the communication primitives at the partition boundaries to allow data exchanges between the neighboring partitions. So in other words, it isn't up to the programmer to figure out which micro batch is being executed where, and what are my dependencies, and do I need data from this certain micro batch which is running at this particular accelerator. No, GPipe does all of that for you. GPipe automatically recomputes the forward activations during the backprop to further reduce the memory consumption. So it's not just pipelining, they're actually recomputing activations. The gradients are consistently accumulated across the micro batches so that the number of partitions does not impact the model quality. And the idea here is if we change the size of our mini batch, so if we're doing mini batch gradient descent and we change the size of the mini batch, that actually has an impact on the training. So what GPipe or the authors here are essentially saying is that the gradients are actually accumulated across and they're updated at the end of the micro batches so that all of this, what GPipe is doing is actually transparent to the data scientist who's actually training a model. Okay, the partitioning algorithm. So in other words, how does GPipe actually partition the problem amongst the workers? That is heuristic based. Currently, it simply minimizes the variance of each composite layer's estimated cost. This is something that I have not gone into too much detail exactly how they do it. They do say that this is a fairly straightforward thing right now, and that better partitioning algorithms in the future would actually make GPipe better. Some results. So they have run two different, so there's ResNet 101 and the AmoebaNet. They've run two different models, and they claim that they observe almost linear speed up in training the AmoebaNet. So for example, AmoebaNet needs at least 2 to start with. You cannot train it on 1. And so the baseline is the naive 2. And then if they use 2-level pipelining using GPipe, then they get a minor improvement. But as they go from pipeline 2 to pipeline 8, the speed up is 3.5x. So that's pipeline 2 to pipeline 8 is a 4x larger. So you're going from 2 accelerators to 8 accelerators, and they get 3.5x speed up. So near linear. The improvement, so speed up, for example, for AmoebaNet is 3.5. The speed up for ResNet 101 is actually a little less than 3. So the speed up, ResNet does not speed up as much. And the reason for that is there is overhead associated with actually using multiple accelerators. There is overhead. There are multiple different overheads, and I'll talk about that in the next slide. But the overhead for a smaller model like ResNet is a higher percentage than the overhead for a much larger model like AmoebaNet. So this talks a little bit about overheads. You've got, so the light blue, the 65.6, is the actual computation, and this is the useful work that is being done. the mustard color here, the 22.5, is the recompute. So this is the forward activation recomputation. And that is a significant portion of the overall compute time. Now, this is required to reduce the memory requirements, to reduce the memory load. In case of 4 partitions, then you see that load imbalance is the next largest impact, followed by the bubble. So anyway, so as you can see, that going from 2 partitions to 4 partitions results in a fair amount of, I mean, at this point, you've got only 54%, so a little over half is useful computation. The rest of it is overhead. So in summary, why GPipe? So the authors say that as we go to bigger and bigger models, there are accuracy improvements, and it is possible that we would obtain further increases or further improvements in accuracy by increasing the scale of neural nets beyond the limits of accelerator memory, as well as bigger data sets encourages giant networks with higher capacities. So there is definitely a push towards bigger nets, more data set, more data. So far, apparently these things are now reaching the point where it's limited by the memory in the accelerator, and so things are slowing down. And GPipe is Google's approach, or Google's attempt at solving that problem, or at least pushing it out a little bit further. So Google needs to support larger networks, and GPipe currently can support up to 2 billion parameters with 8 accelerators. And that's all I had. So open this up to questions.